Welcome to the lecture number 4 of our series. And last time we have proved this result about the construction of traces on weak trace class ideal using the functionals, shift invariant functionals as class invariant functionals or L infinity on the space of bounded functions. So today we will start with classification of traces, or rather we will see how the properties of traces and the functionals, the functional gamma correspond to each other. So let's start with summarizing what we have here. So the first, that will be example. The first example is just a restatement of this theorem. It tells us that gamma is S plus invariant if and only if the corresponding functional tau is a trace. That's just the restatement. So the second example, if we take gamma to be continuous, this holds if and only if the corresponding trace is continuous. Or bounded, because they're both functionals. This follows directly from the fact that the operator D is a bounded operator from L infinity to 1. The next example is if gamma is a positive functional, then the corresponding trace is also positive. Number 4. If gamma is continuous and gamma of the sequence of ones is 1, this holds if and only if tau is continuous and tau this 1 plus 1 is lower than 2. Let's show it now. So tau of 1 is nothing but gamma of, and I will write this sum as a difference of two sums. And now we will use, so let me write it first. I will write it as log of 2n plus 1 minus log of 2n. Okay, and finally I figure out what's going on here. So we don't need the continuation. Yeah. Sorry about that.
There is a typo there. K plus 1 instead of N plus 1.
Yeah, correct. Thank you. Sorry about that. And what we have used here. So these asymptotically behave like logarithms.
Yes.
But so technically we can write these plus something which is vanishing, so C0 sequence. So what we use here is that every S plus invariant function is S minus invariant on L infinity. That's what we have proved in the first lecture. And every S minus invariant function will vanish on C0, because C0 sequence go into 0, so the terms are less, getting less and less and less. Using S minus, we can shift it, and so it will be eventually smaller and smaller and smaller. So every S minus functional, and also we use here that every S minus invariant function vanish from C. For some reason I went vertical. Yeah, so that's what we have. And then of course it equals to gamma of log 2, which is log 2, because gamma of a constant sequence of ones equals to 1. The next example is number 5. We will wrap together some of these examples. So, and we will go another way around. The trace tau is positive normalized by normalized I mean this. No. By normalized, I mean this. So typically, normalization means that tau of this operator equals to 1. So that's a standard way of normalizing traces. I will go with this non-standard way of normalizing to avoid unnecessary constants. So to get 1 here, I just need to define, I just need to divide by 1 on log 2 in this formula. So it will be the same story, but this formula without logarithm will just nicer. So to avoid this unnecessary constant, I will go with this non-standard normalization. So this will be our definition of normalized trace. If tau on this operator equals to log 2, we will say that tau is normalized. Yeah, and of course for every ideals, the normalization is different. It's convenient to choose normalizations. Okay, positive normalized trace on L1 infinity. This holds if and only if gamma is also positive, also normalized, and S plus invariant. That is, how do we call the functionals which are positive, normalized, and shift invariant? Bad limits. I use this fancy B for bad limits.
Maybe you can either some probably the trace tau is positive normalized or trace. Okay, trace means the traceability rate.
Yeah.
Yeah.
So trace means that it's S plus invariant. Positivity transfer, normalization transfer through these correspondence. So the class of positive normalized traces on L1 infinity corresponds to the class of Banach limits, which are particularly well studied.
So from the this property, we can always get that tau of AB equals to tau of BA. So can we get similar thing from the first property?
From which property you getting that tau of AB equals?
The first one.
Yeah, the first one.
Yeah. Can we get that the tau of AB equals to tau of BA?
Yes. Yeah, that's equivalent. That's equivalent statements.
Okay.
So let me also write it here. All equivalent. Tau of AB equals to tau of BA for every A from the ideal and B then.
Yes.
So these are the equivalent.
Example number 6. Here I will claim that if tau is a Dix-Mear trace, then the functional gamma is of a special form. So tau is Dix-Mear trace. If and only if gamma equals to theta composed with the Cesaro operator, the usual Cesaro operator, where theta is just an extended limit on element and on element. So such Banach limits, well, this is still a Banach limit. It can be checked directly because every extended limit is positive and normalized. So we only need to check dilation S plus invariant, so shift invariance, and it follows from the telescoping property of the Cesaro operator. You can check it directly, it's just a one-line proof. Or we can go around. So we know that Dix-Mear trace is positive and normalized trace, but for every positive and normalized trace, the corresponding functional is Banach limit from path 5. So we do know that this is a Banach limit, and this is a Banach limit of a special type. Such Banach limits are called factorizable Banach limits. And it was shown by Raimi somewhere in the 60s, I do not remember, that the class of factorizable Banach limits is a proper subset of the set of all Banach limits. So as soon as we establish this result, we instantly get that the class of Dix-Mear traces is a proper subclass in the class of all positive and normalized traces. So I will not prove this rigorously. For the rigorous proof, I refer you to this paper, but I will give you a sketch of the proof. C is the Cesaro
operator. Last time
Yeah.
you mentioned.
Yeah, let me recall it. So it's an operator on L infinity given by.
你觉得它这个东西像什么东西？我问你。
So it's just the arithmetic operation.
这个东西像什么东西？这是学校的。
它的零度成频率是吧？
对，像它这个你看算子，它的那个算子， I didn't say that it's similar to the Hardy-Littlewood operator.
Yeah, so it's a discrete version of the
Yeah,
Hardy-Littlewood.
discrete version. That's a continuous version. Because she has a paper and she used the Hardy-Littlewood operator.
Yeah, we will see the Hardy-Littlewood operator in approximately 10 minutes. It will appear in our considerations. So first of all, there is a natural embedding of sequence L infinity into the function L infinity. L infinity of functions on semi-axis, which of course given like this. It equals to xn, that's the function of t. Xn for every t between n and n plus 1. So out of a sequence we just make a step function. And again, since I'm giving you not the rigorous proof but rather the sketch, sometimes I will, or pretty much everywhere, I will not write pi, but we will just think about sequence as a function. So, yeah, I forgot that. Before that, I need to state the theorem. Unfortunately, I'm being very far. So this theorem is due to Alexander Sedaev and Fedor Sukochev. It's in GFE. And I think it's 2012 or 2013 or something like that. I don't remember the year. So, and also I will state a very particular form of this theorem relevant to L1 infinity. For every extended limit gamma, the functional tau gamma of A equals to gamma 1 over logarithm n plus 1 sum k from 1 to n mu k A, where A is a positive iterator from L1 infinity, extends to a Dix matrix. On L1. So what is this theorem about? Typically, in the construction of Dix matrices, we need to assume that this extended limit is dilation invariant. They proved that working on L1 infinity is not necessary. So every extended limit generates Dix matrices. So on L1 infinity, Dix matrices can be constructed without assuming any dilation invariance of the extended limits.
And extended limits
On L1 infinity. On L1 infinity. On sequences. Well, we can equally assume that it's extended limit on functions, and then simply embed this sequence into functions. It doesn't change this. That's what we will use. Before we go further, that was the first thing. That was the zeros thing. We need the second thing. On L infinity, the L infinity of functions, and that's actually the reason why we will think about sequences of functions as functions. Because on functions there are two very nice operations. The first of them is exponentiation, it's a function of t given by x of 2 to the power of t. And the logarithm. On sequences, the exponentiation is also defined, but there is a problem with logarithms. So, being more precise, I have to say that, in fact, so I said that x is like this. In fact, x from L infinity of 0 infinity to L infinity of 1 infinity. Because when t is 0, we get 1. And the logarithm works another way around. Which makes in particular to be this operation well defined. But since we always use these operations under the extended limits, and extended limits vanish on finitely supported sequences of functions, it doesn't matter for us. So I stated that for rigorosity, but it doesn't matter for us. Okay. Few more words about how these two operators work. So it works not by replacing the argument of t by 2 to the power of t, but rather it works by replacing every single t by 2 to the power of t. So let me give you an example to clarify this. So if x of t is, say, cosine of pi t squared, then if we take the x of it, and it's not just the replacing of the whole argument here by 2 to the power of t, but simply replacing t by 2 to the power of t. So it will be cos pi 2 to t. So let tau be the expressions. That is tau of A for positive operator A. That is here for positive operator A. We have gamma of 1 on the logarithm t n plus 1. Over the sum from k. Let me go from 0 here because we're indexing sequences from 0. For some extended limit. What I will do now is I combine gamma with logarithm and apply the exponentiation to that sequence. So it's 1 on n, or plus 1 if you wish, sum k from 0 to 2 to the power of n, mu k. Yeah. Yeah, so let's work backwards. So the logarithm works like replacing every t with log t. Yeah. So we're thinking about the sequence as a function. So instead of n, I need to write log n. So here it will be log n plus 1, which eventually behaves like this function. So this log n plus n tends to 1. So since gamma is its standard limit, it doesn't matter for us. Here we will have 2 to the power of log n, which is n times log 2. So this log 2 looks like making a problem, but in fact we also can get rid of it. So let's go further and rearrange this one. Well, several issues here. First of all, the sum was up to 2 to the power of n. Now the sum is up to, the last index is n, so it's up to 2 to the power of n plus 1 minus 2. Well, first of all, this minus 2 term doesn't change the story, because all mu k tends to 0. This is the extended limit. We can add them, we can subtract them as soon as there are finite linear. Then the sum was up to 2 to the power of n, and here we have up to 2 to the power of n plus 1. So we have one of these bits, one more. But we have shown that this sequence is bounded. But here we divide by n plus 1. So bounded sequence over n plus 1, it will go to 0. So again, it doesn't change the story. But how can I write now? This is nothing but the Cesaro operator applied to this sequence. The only thing we need to do now is we set gamma composed with logarithm to be theta. And this is the extended limit. Yeah, we're actually setting another way around. We're setting theta to be this. And this is the extended limit because since gamma is extended limit, logarithm just changing the scale. If the function tends to say 0, then the function combined with logarithm still tends to 0. And then we obtain that this equals to theta composed with c of this sequence. Which is exactly what the plane result. Again, here it should be interplay between the extended limits on sequences, on functions, but again, kind of sweeping this under the carpet, giving you the general idea of the proof and referring to the original paper if you're interested in that. Any questions for this? Yeah.
So, gamma composition belongs to extended limit.
Yeah, correct. Because this composition gamma Oh, sorry, not gamma logarithm. So this composition, it doesn't change the limit. So if the function x was convergent, then x composed with logarithm is convergent as well to the same number.
That's because log is slowly varying. It tends to infinity.
Yeah, it tends to infinity. That's what we need.
Yeah.
The variation doesn't matter. So, for instance, if instead of logarithm you will take t squared, so it's not slowly varying, but it still doesn't change the limit. So as soon as we replace the argument with some function, or rather, if we have a function and we take its composition with the other function, if that second function tends to infinity at infinity, then this composition doesn't change the limit. So that's the only thing we need to ask for the second function. It goes to infinity. Yeah, at infinity.
So indeed, you don't need to choose log t. You actually can choose other function to replace log t, right?
Well, in general, yes, but to make this working, I need logarithm because I have logarithm here,
Okay.
and I want to get rid of it.
Yeah, because I remember you can consider the m phi, right? Not
Yeah.
just
Yeah.
and here if you when you take phi equal to the log, let's say this just this type. But if you consider the logist idea, the m phi,
Yeah.
then the log plus 1 is replaced by some concave function.
Yes.
And slowly varying as
Yeah.
infinity.
Yeah.
And in that case, can you get a similar result?
Yes, that's a recent result of myself and Galina Levitina, and I'm planning to speak about that next week.
Okay.
So it will be, for that case, it will be the generalization of the Cesaro operator, which can be, which is properly termed as a Riesz operator. Riesz operator. Or you can think about them as weighted Cesaro operators, so Cesaro operator with weights. The example number next. Next example. The next example, so in the previous example, we specified the classes of Dixnier traces and corresponding functionals. Here we will concentrate our attention on the class of Kohn-Dixnier traces. So, Kohn-Dixnier traces are just Dixnier traces for which omega is given in the special form, where gamma is just an extended limit, and let me go with this as m1 m bar of x is so it's kind of an analog, not analog, but contrapart of the Cesaro operator. It's some kind of a logarithmic Cesaro operator. Now we will find describe a subclass of S-plus invariant functionals corresponding to the Kohn-Dixnier traces. So again, I will give you the sketch. So we will think of sequences as functions and so on. So to simplify this stuff, instead of the discrete version of the operator m bar, I will define the continuous version.
What's the relation between the Cesaro operator
continuous level, on the level of functions. So first of all, let's consider m of f of t to be 1 on log t integral from 1 to t x f of s ds on s, which is the continuous analog of this operator, because this denominator behaves like logarithm, and this is pretty much, this is the continuous analog of this sum. And also consider the Hardy-Littlewood operator. And now let's see what happens if we compose m with logarithm. This is nothing but 1 to t f of log s ds of s. Because how does it work? We first apply logarithm to f and then apply m. Let's make the change of variables. S equals to 1 goes to z equals to 0. S equals to t goes to z equals to log t. So we obtain 1 on log t from 0 to log t f of s ds, which is nothing but the logarithm combined with h of f. That's the relation between m and h. They are intertwined by logarithm and the exponential operators. Yeah, well, let me, so far I showed this. But we can write it in the other way. So I just apply x from the left. So that's what I mean by intertwined. Now let's take a Condixmere trace. I use this notation for the class of Condixmere traces. And let A be a positive operator. We have, since every Condixmere trace is a Dijksmere trace, then we have a tau of A equals to, instead of omega, we have in, well, not this expression, I will go with the continuous version of this operator. Now, I will go with it even in a simple way.
So when you compose the omega here with the log function, then actually you got similar.
that's what I'm about to do. So I wanted to go through the proof, but then I realized that I proved a lot of it already, so I will just use that to simplify the proof.
I mean, when you compose omega with the log,
Omega?
with the log function,
Yeah.
then actually it becomes gamma, the composition of gamma and the H.
Yeah.
So it's something similar to,
Yeah, we
So
will,
then-
we will get an extra C.
yeah.
So, for yeah, okay, let me write it as I want you to write it. So that's what we have. Repeating all the previous proof for Dixnian traces, we get that it is gamma n logarithm of C applied to this sequence. So we can repeat that, or we can say that every Dixnian trace is Dixnian trace, so we can use that result. So now we have just shown that it equals to this. Yeah, considering what I'm writing here, I have to write in the letters here that it's a sketch of the proof. Because it's too non-rigorous. Because now what I'm going to do is, we have the discrete Chisara operator and the Hardy-Littlewood operator, which is the continuous version of the Chisara operator. I will just replace these by C. So the rigorous explanation for this would be that Hardy-Littlewood operator of the pi of x, pi is the natural embedding of sequences into functions, minus pi cx belongs to C0. So that's the rigorous explanation of that. So what we're having now is gamma logarithm C squared applied to this sequence. Well, gamma is extended limit. Gamma composed with logarithm is also an extended limit. So the result we proved, tau is a Dixnian trace. If and only if the corresponding functional gamma can be written as theta composed with C squared. So two Chisara operators. For some now let me explain what we can get from it, or rather what we wanted to get from it. So a couple of lectures ago we have discussed the measurability. So let me just recall you the notation. of the terminology. An operator A, let's set it as a definition. An operator A from L infinity, from L1 infinity is dx measurable if tau of A equals to C if there exists constant such that for every tau from the class of dx matrices. So an operator is called dx measurable if all dx matrices take the same value. Similar definition for the con dx measurable. There exists constant such that all con dx matrices take the same value. So having defined the dx measurability and con dx measurability, I will cite a result from Lord Sedaev. Sukochev, of course. Almost every result from O5. So they proved that, although they, I have already mentioned that the classes of dx matrices and con dx matrices, they are distinct. But regardless of that, they proved that, I will state the particular form of their result. An operator which is positive and from M1 infinity is dx measurable even though it is con dx measurable. So although the classes of dx matrices and con dx matrices are distinct, if they coincide on a positive operator from M1 infinity, then they do it simultaneously. Well, it was a natural question, is this true for non-positive operators? And the modified pitch construction can answer this question. But before that, I have to state some auxiliary result. Because before that, we constructed, well, not before that, we have constructed the dx matrices, we have constructed traces, but the formula is given in terms of the singular value function, and the formula is given in terms of singular values. And first of all, we define the operator on the positive cone, and then extend by linearity. So this is not suitable to treat, not good enough to treat the arbitrary operators. So to treat them, I will state the result, which is called the Lipsky formula.
I have a question
Yeah.
here. We already know that dx matrices is a subclass of the con dx matrix is a proper subclass of dx matrix.
Yeah.
And the definition of dx measurable is for any trace in in that class,
Yeah.
you have that it's there is some constant such that trace of A equals to C. So.
Well, yeah, so what you're probably asking about is that this implication is trivial. So if it's Dixmuir measurable, then it's non-Dixmuir measurable.
Yes. Yes.
But the question is about the other one.
How to get the whole, how to get the whole class from a subclass, and it's a probe subclass.
Yeah.
It's actually a little weird to me.
Yeah.
So actually, the
let me try to explain that as follows. We will need this result anyway. So we know that if the sequence X is convergent, well, let's say to 0, it doesn't mean. Or better, let me write that it's just C0. Then C of X is also C0. The Chizar. Because the Chizar operator takes the averages, and so it will go to 0 anyway. The smart way of explaining that is because the Chizar summation is regular method. Well, regular method means that it maps convergent sequences to convergent sequences and the limits are the same. So it's just a smart way of saying this. So this is what we always have, but Cx being convergent does not imply that X is convergent. And this is a very simple example. Just take X and to be 1 if n is 2 to the power of k and 0 otherwise. So this sequence is not convergent to 0, but it has ones so rarely. So it's huge blocks of zeros and then only 1, 1. When you will take the arithmetic mean, the Chizar mean, then the sequence will go to 0. But under some extra condition, this implication holds. And this condition is typically termed the Tauberian condition. So that's the theorem by, well, it's called the Hardy-Tauberian theorem. If we have a bounded sequence y such that n times yn minus 1 is bounded from below, if it's bounded from below, then Cy convergent if and only if y is convergent. So in general, this implication does not hold. But if our sequences are nice enough, then we have this implication as well. Another point to add here in attempt to remove your confusion is that this implication cannot hold for any x. Because if we suppose that it does hold for any x, then convergence of x is equivalent to the convergence of cx. And cx, then the operator c is nothing but identity. Well, maybe plus c0. Yeah, so something like this. So then the method of summation is trivial, so it coincides with the usual convergence. So it doesn't tell us anything. So yeah, this Hardy-Tauberian theorem tells us that although this implication cannot hold for any x, on some subspace or subclass of sequences, of bounded sequences, exactly those satisfying this condition, Cesaro convergence equivalent to the usual convergence. Okay, so we will use these results to prove this theorem for arbitrary A, but so far we are not ready to do that. So the one result we need is so-called the Litsky formula. That's also was proved in this paper. So today, pretty much all results are from this paper. The formula is let lambda k be the sequence of eigenvalues from 0 ordered such that the absolute values of this sequence are not increased. And so we order them in such a way that the absolute value is decreasing. For every trace on L1 infinity, we have L of A equals to, well, we didn't gamma. Gamma, the corresponding function of the same dyadic sum. Okay. But now there are eigenvalues here, not the singular values. And now this holds not for positive operators, but for any of them. So this Litsky type formula shows us that any trace on L1 infinity can be computed in terms of the eigenvalues of the operator using exactly the same formula as for the singular values. Say again? Yeah, gamma is. No, it's not necessarily expanded limit. With gamma being shift invariant, linear functional, shift invariant and linear functional. So the dual of calculation. So it would be an extended limit if besides that, if it's positive and normalized, then it's extended limit. But since we not restricted consideration to positive normalized traces, but rather consider all possible traces, what we can say about the gamma is just shift invariance.
What time did you announce this result?
In the same thing.
What time?
What year?
Yeah, what year?
I think it was published in 13. Yeah, 13. Yeah, that was yeah. So it was pretty much it was published and I finished my PhD.
I saw these results for classical case, for standard trace on BLH.
Yeah, that's the original result by Victor Litsky.
This size, it's hard to prove.
Yeah, the original result was extremely hard. So proving this result, we had a quite developed theory of that. So this result proved in several short propositions, which maybe takes 1.5 pages. Yeah, and it's still the heavy machinery behind that was proved in the book of the singular traces book. Yeah, so it's in fact it's very non-trivial result, even for the classical trace. Okay, so now having this result, we can deal with not necessarily positive operators. So we do access to not necessarily positive operators. We want to prove that tau A equals to C for every tau from D, and tau A equals to C for every tau from con D. So this is straightforward because of the inclusion. This one is not clear. Equivalently, we know that Dixmian traces correspond to the functionals which are gamma composed with C. Yeah. To C for every extended limit. But if every extended limit take the same value on a sequence, then this sequence is convergent. Because do you remember at the very first lecture, we proved that the values of, yeah, it's probably a good idea to state it. Since this set equals to the interval Vn of xn lim sup of xn, then if all extended limits take the same value on a sequence, then this sequence is convergent. Because if this is a single point, then this is a single point as well. So this result can be restated if and only if C of this sequence belongs to C, convergent. So for Ondixmere traces, the corresponding result will be C squared of this sequence is convergent.
Okay.
Is convergent. And again, we clearly have these because if this convergent, applying one more C is still convergent, but this one is not clear.
Using that.
Yeah, the Hardy-Tauberian theorem. So now it's time to state the theorem. An operator A from L1 infinity is Ondixmere measurable. If and only if A is Dixmere. Proof. Set Y to be C of X for some down X. We have n times yn minus yn minus 1 equals to n times cx n cx minus 1. Now let's use the definition of Shizar operator. From 0 to n minus 1, xk minus n over n minus 1 to n minus 2 xk. Equals 2. So I will take this sum up to n minus 2. I have it here and I have it here. So from here I'm having 1, from here I'm having, let's write it as it is. Plus x and minus 1.
Yes.
So it is
Minus 1 minus n. 1 over 1 minus n.
say again?
1 over 1 minus n.
1 over, yeah, 1 over n minus 1.
Then you need to put minus.
Minus plus, yeah, minus, correct, yeah.
Okay. Yeah.
Which is greater than or equal to minus 2 log x. Because in this sum there are exactly n plus 1 terms, and it's n plus 1 here.
Yes.
So the condition of the Hardy-Tauberian theorem is satisfied.
Yeah.
Therefore, C y is convergent if and only if y is convergent. But our C, our y is Cx. Therefore, C squared x is convergent if and only if Cx is convergent for every x from infinity.
Yeah.
This one does not hold for every x from L infinity, or rather for every y from L. This one does not. So here we suppose that y is in a special form, in this form. But this statement holds for any exponent infinity. And well, what can we say now? Since this sequence belongs to L infinity, we are done. The assertion false. And so on L1 infinity, the conditional measurability is equivalent to the experiment. Also, probably worth to add a couple of remarks about this property of Cesaro operator. So it tells us that if the first application of Cesaro operator is convergent, well, that's trivial. If the first application is convergent, then all the rest are convergent. That's the trivial one. What is more important, it tells us that if the first application of the Cesaro operator is not convergent, then it doesn't matter how many of them we apply, we will never get to the convergence case. So it's kind of an interesting operator in the sense that it either sends a sequence to convergent in one go or never.
So, why do you need this theorem? I mean, there, you wrote the trace equals to in that way. But using the original.
But the original
one
theorem.
Yeah.
In the original theorem, we have the traces given like this.
So not composed with the Cesaro operator.
No. It still can be composed with the Cesaro operator for these traces.
Yeah.
But the most important thing that it's for positive operators. And after that, we extend it by linearity. Like we want to treat it in one go.
So that formula cannot is not true for all A, only for positive agents.
Yeah, that's true. That's true. Even for the self-adjoint A,
it's not true.
the formula cannot be written as. So the formula is written as sum of mu k A plus minus mu k A minus. So that's the extension by linearity. So in this case, for instance, if both A plus and A minus are Dixmier measurable, then A is Dixmier measurable. But it's not guaranteed that we cannot conclude from the measurability of A, we cannot say that both A plus and A minus are measurable. That's not the case.
So what's the problem to get from the general result from the positive result? So what's the problem? You can always split the general operators into four.
That's what I'm speaking about. Let's go with the self-adjoint case. So what I was. So from LSS, we know that a positive operator from L1 infinity, or positive operator from L1 infinity, demeasurability equivalent to CD measurability. Now let's take A to be self-adjoint. So A equals to A plus minus A minus. And let A be CD measurable. But this does not apply that A plus and A minus are CD measurable. So we can apply this result only to A plus or A or A minus, vertical minus. Only either these or these, but from measurability of A, we cannot say anything about the measurability of the components. I can try to give you a simple example of these, not in terms of measurability, but in terms of the convergence of sequences.
I think I believe this.
Oh, well,
Because the
yeah, I
is
can make you not just believe, but know. So let's take X to be 1, 0, 1, 0, and then Y to be 1, 0, 1, 0. Then X minus Y is identically 0, so it's convergent to 0, but none of these are. No, that's boring. That's boring. equal to 0, that's boring. No, we shouldn't go like this. Let's take to be 1 plus 1 on n. To be this when n equals to 2n plus 1. So at all odd points, we have this. Then the difference is either minus 1 on n, if n is odd or 0, so it's convergent to 0. That's less boring. So they're pretty much the same story. So here, in this similar fashion, you can construct operator A, which is measurable, but none of these components are measurable. So we can use that.